Welcome to this tutorial. Today we'll be using the JMP software student edition to do some linear plateau and quadratic plateau modeling. Our example is going to be this data set here for nitrogen rate response for corn yield. So we have our study, we have our years we're doing this, our crop is corn. We have two locations that we did the study at where we have nitrogen rates ranging from 0 pounds up to 240 pounds per acre. And then these are our yields with those. So we're going to do nonlinear responses to each of these. But in order to do this first, we need to make a few new columns. We're first of all going to set up the linear plateau. So we're going to click over here. So we're in our last column, then we're going to right click here, click on new columns, and we're going to name this linear plateau. Go ahead, these are all going to be the same. It's numeric, continuous, and hit apply, and hit OK. Then we're going to right click on that column and we're going to click on formula. And it's going to bring up this screen right here. And this is where we're going to start to create our formula. So the formula we're going to be using is going to be a conditional formula. It's an if one right here. Click on there. It's going to come in here. And before we start here, we're going to create some parameters. We're going to go down here, go to parameters, and do a new parameter. So in this, we're going to do a linear plateau. So we're going to have three different parameters we're going to input in here. Our first one is going to be our A parameter. This is going to be our intercept, and our typical intercepts for yield of zeros, we're going to say is around 120 bushels per acre. So these are just estimates, just doing your best guess to start. Our second parameter we're going to use B, and this is going to be the linear slope. And we're just going to put something simple. We're just going to put 1, just kind of close to what we want. The last parameter we're going to put, I'm going to label it as JP. This is going to be our joint point. This is where the linear plateau model plateaus out. So that kind of joint point, put a linear and then the plateau. So we're going to name that JP. And that's, we're going to say around 130 pounds of nitrogen per acre is where that's going to go, just an estimate. So now we have our parameters over here. Up here we have our column headers. And now we're going to go ahead and start in here. So we have our if. Now we're going to start with our expression. We're going to say if that nitrogen rate, that x variable, is less than that JP, that joint point, then this is the equation we're going to use. It's going to be A plus B times our nitrogen rate. Else, if it's above that, we are going to do A plus B. And instead of multiplying it by our nitrogen rate, we're going to multiply it by our joint point, because this is at the point where it's plateaued. It's no longer going up. So that is our joint point. That's the simple equation that we're going to use. We're going to go ahead and hit apply and hit OK. So that does that. So we're going to go ahead and analyze this. So we go to Analyze. We're going to go to Specialized Modeling, Nonlinear. Now here our Y response is our Y variable, that response variable. In this case, it's yield. Put that there. Our X predictor is not nitrogen rate at this point. It's going to be that formula that we created, that linear plateau formula. And we do have two sites or two locations we're looking at, and we want to look at them individually. So I'm going to use this site one right here. We're going to put it in the by variable so we can look at them individually and not together. Then we're going to go ahead and hit OK. Once we do that, we have this dialog box that opens up. And we see our data here starts to show up. And this is the model that we started off initially with the initial parameters we put at 121 and 130. And we can do a couple things here. These right here kind of estimate, kind of get us where we want. We can kind of see our intercepts actually closer to 220. This right here is kind of the low and high that we can kind of move things around with. So we can kind of move that intercept to be higher or lower. Probably needs to be around 220. We can kind of move it there. So we're going to move this range over a little bit and move that about there. Our slope looks like it's less than 1, so we're going to kind of move it down there some and just kind of keep moving that. Our joint point looks like it's closer to 100, so we're going to move it down as well. And look at that there, and that's not quite exactly where we want it. We probably need a little bit more of a curve down. It doesn't have to be exact. We can move this. Say we want that range a little bit lower just so we can kind of look at that a little bit more. And it doesn't have to be perfect, so we're going to go up here, we're going to hit go. This is going to start at the iterations and try and figure out where it does. So this one converged in gradient. If it doesn't converge in gradient, you can increase the stop limit, you can lower some of these, or sometimes you have to go here and look at the data and say, actually, some of these might be outliers, which might be influencing that. So then we can scroll down here. That was for our first site. This is our second site. If we're like, well, we just want to see if this works, we can just hit go, and sometimes it'll go about where we want it to. And if we think that looks representative, we do maybe have like these points right here. If we think, well, that one's kind of an outlier, we can click on that point, and then over here in our spreadsheet, we can scroll down until we see that point, and then we can look at it in context of the other ones to see if that is an outlier or not. If we think it's an outlier, we can hit hide and exclude, and it'll go away. It'll go out of there, and then we can hit go again. You can see it kind of changes it a little bit there. If we think it is, we can kind of mess around with those. And here we see these parameters right here. We can kind of get them. If we want some confidence limits, we can hit here. This is 95% confidence limits, and we can edit that as well if we'd like to. But here we get confidence limits there. We don't get them for all of them, so we might need to mess around with some of the convergence or lower the alpha there that we want there. So this is our linear plateau. Now that we've kind of gone through the linear plateau formula, we're going to do that same set of processes, but now for the quadratic plateau. So we're going to right click here, add new columns. We're going to name this quadratic plateau. All the other settings are the same. It's numeric continuous. Right there, go ahead and hit apply, hit OK. Right click, formula, and now we're going to go ahead and start working on the formula for the quadratic plateau model. So we're going to go over here and go to conditional, click on if statement. Now we have this here. We're going to go ahead and start this. For here, we're doing our typical quadratic plateau formula. So a plus b times n rate plus c times n rate squared. So we're going to go ahead and set that up. So the first thing we're going to do right here is make our constant or our parameters in here. We're going to have 3 of them. So our first parameter we're going to say is a, and that's our intercept. And just put that at 120. Next one is going to be b, and that's going to be our linear term. So we're just going to leave that at 1. And then our final parameter is going to be c, which is the quadratic parameter, and this is going to be negative. We're going to do 0.0001, just kind of as a starting point. So now we're going to do this. We're going to do the conditional first, and this is if the n rate is less than that joint point from where that quadratic point goes to a plateau model. And there are several ways to do these. I'm just going to show you the one that I do. There's different ways to do it, but this is just the one that I use. So here we're going to do similar as last time. We're going to say n rate less than that joint point, and the equation for that joint point is a little complicated that I'm going to use, but it helps with some of the other, with getting the right data in there. So we're going to do a negative sign right here. I'm going to put parentheses in. Within that parentheses, we're going to have b. And then we're going to make sure we click on the box so it's that whole box is there, but not the negative sign. And we're going to click on divide. And then we want parentheses down here as well. And this is going to be 2. So we're going to hit 2, enter, and then we're going to do times c. So this is basically the equation for the joint point for the quadratic plateau model. So if the n rate is less than this, we're going to do the quadratic plateau model, which is going to be a plus b times n rate. And here, if we just hit plus again, we're going to get parentheses automatically, which is not what we want. So we're going to make sure we click on the right box so we're getting the right thing there. And we still got it there. So sometimes you just kind of have to fiddle around with which set of numbers you have it around. So then we get that. That's what we want it to look like that. Then we're going to go C times, and this is going to be n rate squared. And make sure it's on that box. We're going to click up here, this x to the y. That's going to put the power, and just put a 2 in there, hit enter. So this is if we're less than that joint point where the quadratic turns into a plateau model, then we just want the typical quadratic model. Else, if it's greater than this joint point, then we're just going to have it be the quadratic, but where the quadratic is just at that joint point level. So to do this, we're going to do a minus b squared, so x to the y, enter there. And then we want this whole thing, so we want the b squared, so we're going to divide that. And then parentheses here, and it's going to be 4, enter, times c. So this is our quadratic plateau model right here. There's other ways to do this. This is just the example I'm showing today. So go ahead and hit apply there, hit OK. So now we've had this here. We can go back to analyze. We can click on specialized modeling, nonlinear. Our y response is going to be our yield. Now our x predictor is going to be our quadratic plateau formula. Again, we have multiple sites, so we're going to do our bivariable as that site one. Click OK. And now we're going to have this one right here, and we can look at the other one side by side. It's something I like to do just to compare the differences. Here's our linear plateau model. We're going to bring it up to the first site. Right here, we can see our data here. And this is going to be fitting the quadratic plateau model. So we can go here and we can fiddle with this, or we can just maybe hope that it'll kind of figure it out. And it seems to figure it out quite well just by hitting go. Hits iteration, hits converged, everything looks good there. So this is our quadratic plateau model. You can see the estimates for the intercept are pretty close to the same, 1.03 for the linear term here, 1.4 for there, but you can see the C term here. We don't have a joint point term in this one specifically, and we'll get to that in a minute. But this is our A, B, and C term because a quadratic model has 3 terms, whereas a linear model only has 2, so we can add the joint point for a third one there in comparison. And just the same as before, if we want confidence limits in there, we can go down here as ABC, confidence limits. We can see sometimes it doesn't do it because it just doesn't converge within that area because some of these are hard to. We can lower this convergence criteria and see if we can get some more. We didn't get any more. We can lower the standard deviation. Maybe this is 2 standard deviations for 95%. If we just want to look at 1 standard deviation, we can type in 0.32. Hit confidence limits, and we can see we get more based on that because it's not so widespread. Now we can move down to the second site and look at it, see what it does. Sometimes sites like this one with a little bit more variability, if we just hit go, it actually did find it here. Sometimes it won't. We have to go down here and kind of create the parameters, move them about where they are, and then hit go and let it kind of find those. So we can see there the estimates. Here, the 181, actually we see here that it didn't converge because we don't get the parameters down below. We can accept the current estimates, iteration options, and things like that. And there might be some outliers. You can see here that these two seem kind of low. And we can look at those to see if that makes sense to not include those here just to kind of show you. And we can say, okay, yep, they're a little bit low, so let's hide and exclude those. So it hides and excludes them, then we can hit go again and see if that helps. It still doesn't converge there where we want it to. We can accept current estimates, or we can lower some of these. So it says it cannot decrease the objective function, which is this one right here. So we can click in there and we can say, okay, let's get rid of some of the zeros so we don't need it to be that exact. Try to hit again, see if it kind of goes in there. Sometimes we have to go in here and let it change a little bit for these to work. So we hit go again, let it kind of do its thing. And then it converges. So sometimes we just have to play with it a little bit. And now we can see the things here. We can kind of see if it makes sense that that's kind of where we would picture it being, which is pretty close. It's not too far away from the numbers we have over here that did converge. So I'd say it works pretty well. And so we can kind of see this along here. It looks appropriate. We can look at confidence intervals. They all showed up here. We can do the 1 standard deviation confidence intervals and change it there if we'd like to. So now we've looked at linear plateau and quadratic plateau. So we have our A, B, and C. Here we have our A, B, and our joint point. If we want to look at a joint point here on our quadratic model, we've got to switch out the joint point in one for A, B, or C in this instant. And the one I'm going to show you is we're going to switch out B and calculate a joint point instead. So then we can look at confidence intervals for it as well. And there's 2 ways to do this. We can do the agronomic one, which is just that maximum point here, we can calculate for it, or we can do the economic one. We'll do each, but just to kind of show you where we're at here. So we're going to go back to our table here, and we're going to do the same thing. We're going to click over here. We're going to do new column. This is going to be we're going to call it our agronomic optimum N calculation. And this is for the quadratic plateau. So we're going to hit apply, hit OK, and then we're going to right click in here and go to formula. So once we have that formula window open, we're going to go over here and go to conditional, click on if, and now we're going to start doing that equation. But first of all, we're going to create our parameters. So we're going to click on parameters, click on new, and here we're going to name them a little bit different. Parameters are going to start with a beta 0. This is basically our a variable or our intercept variable. And we're going to say that one, in this data set, we know it's around 200, so we're going to start there. Hit OK, new parameter, and we're going to go ahead and do beta 2. This is our quadratic term, so we're going to do negative 0.0001. Hit OK. Now instead of doing our linear term, we're going to do our joint point. We're going to call it theta. And we know it's around 70. So we're going to go ahead and use that there. From some of the other stuff we've done, so now we're going to start that expression where if our n rate is less than that joint point. So we're going to click on n rate less than, and our joint point is our theta parameter. We have that there. Then we're going to go to our then clause. So we're going to do, if it's less than that joint point, this is going to be the quadratic portion. And it's going to be different because we don't have that b variable or that linear term. So we're going to start off with parentheses. We're going to say beta 0 minus 2, enter, times theta times beta 2 times n rate. And those are going to be the parentheses. We're going to start after the parentheses now. So we're going to click on that box there, click plus. And this is going to be beta 2 times n rate. And n rate is going to be squared, so x to y. Put 2 up there. So this is there. It's always important to go through and make sure that this is correct. Beta 0 minus 2 times theta times beta 2 times n rate plus beta 2 times n rate squared. Now our else clause is going to be when we're at that plateau portion. So we're going to start off with beta 0 minus, and we're going to do parentheses here. So it's going to be 2, enter, times theta times beta 2, and then we're going to square the whole thing. So x to the y, 2, and then here we're going to divide the whole part right here, so we can make sure that's highlighted correctly. Parentheses, 4, enter, times beta 2. So beta 0 minus 2 times theta times beta 2 squared over 4 times beta 2. So once we check that and we know it's correct, we can go ahead and hit apply, hit OK, and that should show up right here. And now we're going to do the same thing before, analyze, specialized modeling, nonlinear. Our y response is still going to be yield. Our x predictor is now the agronomic optimum QP. So that's our x predictor. We do have multiple sites, so we're going to do a bivariable there. We're going to click OK. So it's going to open up this screen right here, and we're going to compare that here because it's good that once we start having these things, because we don't have a linear term here. We just have we have our intercept, our quadratic, and this is our theta, which is our joint point. So sometimes it's harder for it to find it correctly. So it's good to be able to look over here at our quadratic model to know about what that beta 0 should be around 219. That C term or that beta 2 should be around negative 0.11. And as we said before, you can just hit go and see if it gets in. Sometimes it does, and sometimes we have to go down here and play with these things. It looks like it turned out fine. We converged in our gradient. And we now have our estimates down here. We have our standard errors. And if we want confidence intervals for each of those, for our theta right here, calculates it at 65, which is about right here, which looks about right. We want confidence intervals. So this is our confidence interval that that nitrogen rate that we optimize yield or maximize it is around 65 pounds of nitrogen per acre, but lower confidence interval is between 40 and 89. So we're between 40 and 89 right in here of when we start to do that. If we want a little bit different confidence interval, say we don't know 95%, we just want one standard deviation, we can do 0.32. Hit confidence limits again, and now it updates to that, so we know a little bit more precise. A good range is probably between 55 and 77 pounds of N is where we're optimizing that N rate. So that's agronomic optimal N rate. We can do the same thing. We move down to that second site. We can look at the parameters over here for the linear plateau and the quadratic plateau models. And we see the parameters here to kind of start out with. And if we were hoping it'll work, we can just hit go. And it did work in this case. We don't have to change anything, but sometimes we have to play with these numbers, kind of use them here, get them about right, and then hit go, because sometimes they'll give you like a ski-wampus backwards number, and you're like, that's not correct. So we can go here. We can move these around to kind of get it where we think it actually should be. Maybe it's right there. And then we can kind of hit the plateaus, maybe change some of these a little bit, hit go again. Just want to make sure what the line looks like is realistic. So that's our quadratic plateau with an agronomic optimum, where instead of looking for these variables, you're actually using this theta variable. So now we have an estimate for that theta, that optimal N rate, because that's one thing we want to look at confidence intervals for. Look at it here. These are 95. Again, we can change it because 118 to 210, that's a really big spread. It's 100 pounds of N. So we're just going to say let's look a little too impractical of a number. These data sets tend to be variable. 136 to 180 is a little bit smaller, a little bit more usable as far as talking to farmers and things like that in my line of work. So now we have three that we're looking at here. We have the linear plateau, quadratic plateau, and quadratic plateau where one of our variables is our theta. Now in my line of work, we often want to put economics into this because a quadratic plateau model, the quadratic form increases at a decreasing rate, whereas the linear just increases at the same rate. But another thing we can think about is we want to think about is this will increase at a decreasing rate, but at some point it might not be increasing enough to pay for the extra nitrogen fertilizer that we're putting on, or phosphorus or potassium that we're putting on. We're not getting enough of a yield increase for each pound of N we're putting on. So we want to include that into it and kind of maybe move this down to where it's the economic best rate, where at that point where we're no longer paying for any extra, but we're maximizing that income. We're not losing profit by increasing yield just a little bit. So in order to do that, we can do that. We just have to go back to the same types of things we were doing before. We open up our data set. We have our linear, quadratic, agronomic optimum. Now we're going to look at our economic optimum is what we call this one right here. So we're going to do a new column, and that's going to be our economic optimum N, and this is also quadratic plateau. Same things here. We're going to hit apply, hit OK, right click here, go to formula, and now we're going to start the formula for the economic portion of this. So we're going to calculate the same things pretty close to what we did for the last one, but we're just going to put in some economics into this equation. So it's going to look pretty similar to our last one. Conditional if statement, go through, make our parameters here. Parameters are going to be pretty close to the same. We're going to be our beta 0. We're going to say that's 200. 200, click OK. Another new parameter. This is going to be our beta 2. And this is our quadratic form. So we're going to negative 0.0001. Hit OK. And we're still going to do our theta variable as well. Here, so theta, this is our joint point. And we're going to call this around 70. So we hit OK on that one. So now we have our parameters and our columns. So we're going to start our expression here. So similar to last time, this is going to be N rate is less than theta. And if it is less than theta, this is the equation we're going to use, parentheses. It's going to be a little bit different. This is our beta 0, and we're going to subtract. We need parentheses one more time. And it's going to be 2, enter, times our theta value, times our beta 2. And this is where we're going to start to include economics. So now we're going to go minus. Oops. We don't want them there, so we're going to click on there and get the right one, so we have it all similar. And now this is 0.1. And how we get this is so we're going to take our cost here is 40-cent nitrogen, and we're going to divide that by $4 per bushel corn, and that's going to equal 0.1. Now you can do your economics based on the current price of those. So it could be 60-cent nitrogen, $100 nitrogen, $3 corn, $4 corn, $5 corn, kind of get that ratio there. And divide the price of fertilizer by the price of corn or whatever you're looking at as far as corn, soybean, or whatever it is. And you can get that ratio. What this ratio means is that here it needs to increase by at least 0.1 for it to keep going, or else that economic optimum stops there. So we need at least a yield increase of 0.1 to pay for the nitrogen that we're putting down. So we have that here. And now we're going to the next part of this. So we're going to take that beta 0 minus 2 times theta times beta 2 minus 0.1, and you're going to multiply all of that by the N rate. And then next, we're going to add beta 2 times N rate, and that N rate is going to be squared. So x to the y, 2, enter. So we're going to check this, make sure everything is right, parentheses in the right spot. So parentheses beta 0 minus parentheses 2 times theta times beta 2 minus 0.1. So this can change. You can go in and change it if you look at your economics of whatever you're looking at. Times N rate. So parentheses, plus beta 2 times N rate squared. So that looks correct. So now we're going to go to the else clause. And this is going to be beta 0 minus, we're going to do parentheses, 2, enter, times 2 times theta. So click on the square you want it. 2 times theta times beta 2. So we just do a minus here. It puts parentheses. We don't want that. So we're going to click on, so we're back here a little bit farther. Oops. Right there, and click on minus. And this is our 0.1. So this has got to match the one that we have up here. These should be the same variables because this is the economic portion that's subtracting from. And then we want to square this whole thing. So we're going to put x to the y right there, put in a 2, and then we want to divide the whole thing. So we're going to click on that part, divide, parentheses, 4, enter, times beta 2. So this is beta 0 minus parentheses 2 times theta times beta 2 minus 0.1 squared over 4 times beta 2. So that looks correct. If something goes funny, this is always a good place to go back and make sure your equations are correct. So we're going to hit apply, hit OK. So this now shows up. We're going to do the same aspect here and go to analyze, specialized modeling, nonlinear. Y response is our yield. Our X predictor is now our economic one. Our site is our bivariable. Hit OK. Now it's going to bring open another box right here. And the biggest thing here, we can just start comparing these things right here and kind of using them to help all of our other ones. So we look at all of our windows, get them all to the other sites that we're looking at here to kind of help us make sure we're getting things the correct way. So here we did a little bit more. We can just hit go, see if it works. We can see we kind of get a little funny thing right here. So now we can kind of look over here and say, okay, we want to make sure this gets correct. So our beta 0 is about 219. So we're going to put that in right there. Our beta 2 is about negative 0.11. So we're going to go negative 0.011200152. That's what this is right here. Hit enter. Our theta value is pretty close to this, so we can see right here our equation looks much better. So instead of putting this in, because this is our agronomic one, so we're going to reduce that a little bit, we could put in 65 just to see what it does. We see it goes up here. And then we're going to hit go again. This is pretty close to what we had it. And then we see this looks much better when we kind of use those. That's why I like to do these other ones first, so we kind of get the parameters that we know we can help it guess to. And the economic one isn't very different here because this is a pretty drastic change right here. Our agronomic one is 65. We put in economics, it only drops it down to 61. And we can see here the different standard deviations. We can look at confidence limits. I didn't like it for that one. We can lower the convergence criteria, see if it'll do it again. I didn't like it. We want to not necessarily look at 95% because it might be too wide. We can look at just one standard deviation. Confidence limits, we see it shows up between 52 and 70. I would say that's a pretty good estimate of where that economic optimum could be. So now we have this. We go down to our second site. We're going to look at it all the way through here just to kind of help us out. Linear plateau probably don't need to move, but we can anyway. But we need these parameters to kind of help out here. We're going to hit go. Doesn't look too promising, look a little funny there, but we can know what they should be. It should be about 181, which is what we see here, pretty close. It got that one right. Our beta 2 estimate, this is negative 0.001398,248. Might wonder why I go out so far, but these quadratic terms tend to need to be out pretty well. Theta, we know it's around 156. We're going to just go 160. See what it kind of looks like. We can see it looks a little bit closer. And last time we're going to hit go, and we can see it kind of goes here. And you'll notice it kind of does with the economics. Sometimes it'll go here, and then it'll kind of jump up. And those are just some variability here, and it's kind of hard. We notice it didn't necessarily converge. So here we notice it didn't decrease the objective function. We can play with the parameters some. We know that what this should be because we already had it converge over here. And so we can kind of reduce this a little bit and try this again and go negative 0.001398248. Call that right there. And we know this is around it's probably lower than 156, so we can go 150. And we can see kind of what it starts to do here. Makes it a little funny. We can kind of drive it down there and say that's maybe a little too much. High, we're going to go to 160 just to play with it some. So we know it's somewhere around here. It's probably there. It's just that economic versus agronomic is sometimes why you get this weird line there. So we're going to hit go again. It converged this time because we played with it. Kind of get there. We see this weird part right there, and it happens sometimes. Sometimes you can kind of go here. The biggest thing is, does this make sense? 181 is correct. Negatives 1.00, that's correct. This is 126 versus 156 because this does a slower one. So it's basically saying at 126 pounds of N, we don't increase more than 0.1 after that. This is why this is our economic one. When I look at confidence intervals of that, we can kind of see here 95%. That theta is between 98 and 144. Kind of a wide spread if we want to look at a little bit less like we have the other ones. We can hit there and notice it didn't give us a lower spread there, but we can kind of mess with that. There, just kind of look at differences in confidence limits. As far as that goes there, we see that here. It doesn't stay smooth like these ones do. Sometimes it has this little bit of a jump, but overall we're getting, this is now what we're looking for is that economic one. Right there, so now we have our linear plateau over here, quadratic plateau with our A, B, and C, so our intercept, linear, quadratic. Now we have we added our theta, or that joint point in where it goes from quadratic to plateau. And this is where our theta is our economic value. So when that increase in economics, see in this one it would keep going up like this and connect there. But here it stopped economically increasing, so it stops and it switches to the plateau model, which then jumps it up here a little bit. But typically it would be this same line. It's just saying this is the parameter we're looking for, is that 126. And this is the confidence intervals. So if we want confidence intervals, we can add these thetas in here and get rid of one of the variables here like we've shown in here. So I hope this answers some question, gives you a little bit more feedback about how we can do these models in JMP. Thank you for your time.